This conference will now be recorded.
Hello and welcome everyone. My name is Kristoffer Martinsson and I work as Field Application Engineer at Know-How Solution. In this webinar, I'm going to talk about how you can use Lauterbach's Trace32 and real-time trace to profile and optimize your embedded application. Please remain muted during the entire presentation, and you can use the chat to ask questions, and I will try to answer the question at the end. Before I come into the topic, I will just give you a short background about Know-How Solution. So we at Know-How, we are a Nordic company. We have offices in Sweden, Finland, and Denmark, with our head office in Malmö in Sweden. And we cover the Nordic market and the Baltics. And we supply development tools for software development. We are mainly in the embedded industry. So just a few examples of our tools. It could be compilers and debuggers and testing tools, static code analysis tools, but we also have some other type of tools like CAN interfaces, Bluetooth analyzers, and so on. And these are some of our suppliers that we work with. And today, the tool I'm going to use for my demo part today will be from Lauterbach, so at the top left. And before I get started, I also want to highlight what I will use here in the demo part. So today I'm going to talk about trace, and for being able to trace an embedded system, there are a few things you need. First of all, you need a normal debug system like the one in the picture here. So it consists of a Power Debug module, a Power Debug Pro, which is a universal module that can be used to trace any architecture. And on top of that, you also need an architecture-specific debug cable, and it could be, for example, for ARM or Tricore, PowerPC, or any other architecture that Lauterbach support. So this is the base that you always need, but to be able to use trace, you also need to extend it with a Power Trace module, or a Power Trace 2, it is called. So the Power Trace 2 is a universal module that you connect together with a Power Debug module, and mainly it consists of a large trace memory. So it could be up to 4 GB of trace memory. And on top of the universal Power Trace module, you also need an architecture-specific preprocessor. So the preprocessor is what will support the trace interface that you are going to use on your embedded CPU. So for example, it could be for parallel trace for an ARM or serial trace on a Tricore, etc. These are the base modules. There are also some other alternatives for tracing when it comes to the hardware, and the content of the webinar will also be relevant if you, for example, use a microtrace for Cortex-M. So this is the setup that I am using today for the demo part. So as you can see, I have a Power Debug Pro, a Power Trace 2, and then I have a debug cable for ARM, and I have a preprocessor for ARM. And the board that I will debug here today is an Ultra 96 board, which consists of Xilinx UltraScale CPU. Actually, it consists of a quad-core Cortex-A53 and a dual-core Cortex-R5. But for the demo part today, I'm only going to debug and trace one Cortex-R5. And most of the, I will use an ARM core here during the presentation, and some of the things that I will talk about are specific for ARM, but most of the things are relevant for other architectures that support trace. For example, Tricore, that is heavily used in the automotive industry. So let's start with some basics when it comes to real-time trace. So real-time trace is when you have a CPU that has some dedicated hardware block inside of the CPU that generates trace data during the execution of the CPU. It should not affect the real-time behavior of the CPU when you have this. So that's why it's called real-time trace. So what type of trace information are there? Yeah, there are a few different categories, and I've chosen a few of them here. There are more depending on the architecture, but these are more general and are available for most architectures. First of all, there is program trace. So that is a description of the instruction that has executed. So with this type of information, you can reconstruct exactly what part of the code has executed. And the program trace is available for all our CPUs that actually supports trace. Then the next step here is data trace. So data trace is when you can record the read and write operations to the memory. And you can record the addresses and the data value. So you can see where you read or write to and what data you're reading or writing. So when it comes to data trace, not all CPUs supports data trace. For example, for the ARM cores, the high-end Cortex-A class, for example, Cortex-A53 and so on, they do not support data trace. Some of the lower-end Cortex-A, like Cortex-A5, Cortex-A7, they do support data trace, and the Cortex-R family support data trace, and I'm going to use that today in my demo. And on Cortex-M, there is a limited support for data trace, but there is some support for data trace. And other architectures like Tricore, for example, they do support data trace. Okay, and the next part, when it comes to trace, what it can consist of, I call it here context ID. And this gives you information about task switches. And this is something that is used if your CPU do not support data trace. And context ID, that's the name for it in the ARM world, but there are other architecture that has similar type of trace messages. And for example, in the PowerPC world and Nexus trace, there is called ownership trace message and so on. But it's the similar how it's used and so on. Okay, and on top of the basic trace data, there is one very important thing that you need if you're going to use trace for profiling, and that is timestamps. There are a few different ways how timestamps can be generated, or actually also where it is generated. And the top one here is the external one, I call it. And that is timestamp that is generated in the Lauterbach debug hardware. So when the trace data comes out from the target and is stored in the trace buffer in, for example, the power trace unit, then there is a timestamp added to it. But it could also be a combi probe or a micro trace unit or any other Lauterbach hardware that supports trace. So external timestamps is very good because it doesn't generate so much trace data from the target. Because you don't need to send any timestamps information from the target. But there are some drawbacks, and I will show you this later on because trace data can be delayed in the trace infrastructure inside of the CPU, and then the external timestamp is not so accurate. So to have the best timestamps possible, you need to use cycle accurate tracing. And that is when the trace IP block inside of the CPU, for example, the ETM in the ARM world, generate number of clock cycles that has passed between each trace package. So in principle is that for every trace package, you get the information, the clock cycle that has passed since the previous trace package. And if you then know the CPU clock, then you also know the exact timing. So this is very, very accurate, and it's the best timestamp that you can get for tracing. But the drawback is that it requires a lot more bandwidth out from the target because it generates a lot more trace data. Then there is a third option, which is some timestamp packages. And this is normally that you have some specific IP block inside of the CPU that generates a timestamp package and insert it into the trace stream now and then. But it's not included like for every trace package, but it's included now and then, so it's not so accurate as cycle accurate. But in some use cases, this can be used. Okay, so that was the basics. So now let's come into a little bit with what you can do with profiling if you have trace. The first thing I'm going to talk about is profiling on task level. So meaning that you have an RTOS of some sort, FreeRTOS, QNX, or something else, or even Linux. You can use profiling on task level. But in some RTOS, a task is called a process or a thread, but it's the same concept, so it doesn't matter. But the first thing that you need is, if you would like to profile on task level, is that you need to make sure that Lauterbach support the RTOS that you are using. And you need to have installed the plugin or started a plugin for this RTOS. But the Lauterbach do support most RTOS that is used in the embedded industry. And the next, when it comes to trace information, there are two ways to record task switches. One is to use data trace. So because in every RTOS, there is one variable that points to the current running task. So if you record all writes to this pointer, then you know when there is a task switch. So that's one option. I'm going to show you how you do this later on in my demo. And then the second option is to use these specific trace messages called context ID. That's for ARM, but for example, for PowerPC, these are called ownership trace messages, but it's the same concept. That's the alternative if your CPU does not support data trace. But to do this, then actually the RTOS must be instrumented in a very limited way, so that every time there is a task switch, the RTOS writes to a specific register in the CPU. So, but it's normally a very, very small instrumentation. Actually, in the case I have here, it's only 4 instructions needed to write the task information when there is a task switch. So it's output. I'm going to show you this later on. And one other thing that might be very useful when it's if you only want to profile on task level is to filter what you're tracing. And filtering in this case is actually done in the CPU itself. So in the trace hardware blocks inside of the CPU. So, and it can be used, for example, to increase the recording time and so on. I'm going to show you this in my demo. So now I'm going to show you what this looks like in Trace32. So now I switch to Trace32 and I'm going to just open some windows here. So here is the normal trace window where you control trace, and I'm also going to open the ETM window here because I'm going to use them in this case. So now we would like to profile on task level. And as I mentioned, there are two ways to do it, either with data trace or with context ID. First, I'm going to show you how to do this with data trace. First of all, as you can see, I have a FreeRTOS menu up here, and as you can see here, I have some FreeRTOS tasks. So that's the prerequisite. You need to have the kernel awareness for FreeRTOS, in this case loaded. So I have that. But the next thing I need to define, as I said, when you're going to use data trace for this, you need to record all writes to a specific variable in the kernel. But I don't know the variable name, and you don't need to know it because the debugger knows it. There is a specific function called task.config, and with the parameter magic, it will return this variable for you. And we are going to recall all writes and enable the trace every time we write to a specific variable, like this. And the actual breakpoint, or this is not a breakpoint, this is a trace filter, it looks like this. So here is actually the name of this variable in FreeRTOS, px current TCB. But for another RTOS, it would be a different variable name. So now we have an enabled so that we record all writes to this specific variable. Okay, so let's start the execution. And as you can see here my trace buffer fills up, and actually it fills up very, very slowly here. But we can look at the result. It looks like this. And now I intentionally made a mistake here because this will not work that very well. Because here we see a task switch here. Here we see a write to this variable, and we see the timing here. And here was the previous task switch. And this column here where time here, TI back, that shows actually time between each trace package. And it looks like there is hardly any time, like 20 nanoseconds between the write here. And that can't be true because you cannot have one task switch and 20 nanoseconds later you have another task switch. There are just a few instructions executed in 20 nanoseconds. And this is actually the limitation when you're using the external timestamps, because here if a number of these trace packages packed together and output a little bit later. So in this use case, it's not a good idea to use when you are generating trace data. So with large distance in between or large time in between, it's not a good idea to use the external timestamps. So I'm going to enable cycle accurate tracing here instead by clicking enable cycle accurate here. And then I will make a new recording. And now you will see here is more relevant data here. Here, for example, there was 52 microseconds since the previous task switch. Here is 19 milliseconds, 52 microseconds, etc. So now we see all the task switch here. And of course, what can you do with this information? So you can use the perf menu and task runtime, for example, and use show as timing to have a view like this. So here you see a time scale here, time 0 here at the end. That's when we stop the recording, and then we have recorded like 2 seconds in this case, and we see all the tasks that we have in the system, and we can see when they have executed. And actually we can zoom in here if we want to, for example here, like this, and zoom in to see some more details. For example, you can just check how long did it take to execute this RX task. Yeah, it did execute 22 microseconds in this case. And you can also get an overview of how much time you spend in each task by using task runtime and show numerical. And you get a view like this, and you can sort it if you want to. And then you can see that we spend 57% in a task called Proffer and 42 in idle, and the other tasks are executing very, very little. So here you can get a quick overview of the CPU load of your system. Okay, so this was the using data trace. And as I said, there is another alternative using this context ID, and this must be used, for example, if you have a high-end Cortex-A class device. So I'm going to just show you how it can be done. So I'm going to delete this trace filter that I have here, because now I'm not going to record any data trace. And then I switch to the ETM window here, and as you can see, there is a context ID option here, and I'm going to enable it. And 32 means that the variable this register is 32 bits wide. Okay, but then also the default is always that you always record the entire program information, and we don't need that. And actually, I'm going to show you this. As you can see now, the trace buffer fills up rather quickly. So for when you're going to profile on task level, you don't need a full program trace. So how would you filter your trace if you are going to use context ID? Actually, then you need to know where in your code you write to this register. And I have actually instrumented my FreeRTOS here myself. So I know that it's in a function called T32 magic update. So this is the small patch I've added to the RTOS to make sure that we write to the context ID register, and it's done by this instruction here. So what I will do is that I will create a filter where I will start the execution, turn it on here, and turn it off just after, like this. So now we are only recording these few instructions when they are executing, and that means that I will catch the context switch or the task switch. So I can close that. And again, make a smaller recording. As you can see, the trace buffer fills up rather slowly, but the result is the same as before. So you can either, if you have a CPU that have data trace, you can use that. But if you have a CPU without data trace, you can use context ID, but it requires a small patch of the RTOS. Okay, so that was profiling on task level. So next thing I'm going to talk about is profiling on function level. So for this, you have to use program trace. So that must be enabled, and it is enabled by default in most like all CPUs. And if you have an RTOS, you should also record the task switches. It depends. It's not always needed, but it's a good idea to enable it as well. So you would do it either with data trace or the context ID that I just talked about. When you're recording with program trace, a lot of trace data is generated. So the size of the trace buffer sets the limits of the recording time. And it could be a few seconds or 10 seconds or a minute. It depends on how fast your CPU is running and how the code actually is running, and so on. So, but the recording time can be increased by using streaming to host. So actually, you can actually stream the trace data from the Lauterbach hardware to your PC during runtime. But that requires that you have a USB 3 super speed connection to your PC. Okay, and when it comes to profiling on function level, there are two levels, you can call it, or two ways to do it. You can have a flat analysis or a nesting analysis. Which one you would like to use depends on what you would like to see. But the nesting one is much more detailed. But what does flat versus nesting means? It comes when the Lauterbach analyze the trace data. So with nesting, it will detect all the function entries and exits and so on, and keep control of that. But with flat, it doesn't detect the function exits. It just detects when you are in the scope of that function. And the same is true for interrupts and so on. So for example, if you have a flat analysis and we have a use case like here on the picture, you're in main and then call some function func1, which then calls func2 that returns to func1 and then calls func3 and then returns to func1, which then exit or returns to main again. So if you have a flat analysis, it doesn't detect that there is function exits here anywhere. So for example, if you would ask or check the minimum execution time of this function, it will say, for example, here, but this is not the minimum execution time from entry to exit. It's just the minimum time you spend in the body of the function. And vice versa, the maximum execution time could be something like this. But if you have a nesting analysis, you keep track. The debugger, when it analyzes, it remembers in what functions you are and keep track of the call tree, so to say. So it knows that here is an entry of the function, here is the exit. And here's an entry and here is an exit of func1. So if you check the maximum execution time of funcmax, the maximum execution time of the func1 function in nesting mode, it will be this time here. And here is the minimum. And of course, this is also the case if you have interrupts and so on. If an interrupt would occur here and you will execute some interrupt routine and so on, it will still keep track of this maximum execution time, so to say. And actually, there could also be a task switch here in between as well. But with flat analysis, you have no idea about that. So with flat analysis, you don't know how long it takes to execute the function from entry to exit. But with nesting, you do. So let's switch back to trace32. And I'm going to close some windows here. And I'm going to delete this trace filter. So for profiling